Okay, we're going to soon start with our last talk for today. We're actually going to record TV, maybe not everything, but a lot apparently. And Philip is going to introduce us in the world of magical TV.
Hello. Yep. Hello. Can everyone hear me? Yep. Oh, maybe not. So is that better? No. Let's try this. How about now? Is that okay? Yep. Okay. Great. So first of all, before I get started, I'd just like to say thank you to Philippe for inviting me along here and for running the dev room for so many years. I've been coming to FOSDEM since about 2003, and I've not really missed many years. So I really just want to say thank you to all of the volunteers, and it's a real honor to be here talking and to finally sort of give something back, as it were. So thank you, Philippe. And so today I'm going to be talking about how to record all TV. So I work for a company called Prospero Technology, and we're just a small R&D outfit based in West London. And we started off by creating an 8-tuner DVB-T PCIe card. Now, this is one of our boards that we made. This is just a 6-tuner version, but they are real. They do exist. They're down here if you want to come in and have a look afterwards. And the 8-tuner card is fitted with a hardware demux and raw infrared support. Now, I was quite pleased with the raw infrared support because I pushed for that, and effectively what it means is that rather than us fixing in one remote control, it means the infrared is passed up to the kernel, and it can then go up to user space to LRRC, or you can then write your own key maps into the kernel. So it's quite handy if you want to put in your own remotes. And we've then been building the same technology into a DVR, which we call Store, and that constantly records 30 channels. So we've got several of those in our offices, all recording 30 channels. Now, I'm just a software guy, really, so please try not to ask me any difficult hardware questions. But this is essentially our software overview. So, as you can see, it's a very simplistic overview, but I've been working on the two outer layers. So we've got the Qt HTML5 user interface using GStreamer, and then we've got the kernel driver, and those are the parts that I've been working on. I won't really be talking too much today about the recording software that we use. So this is a photo of our current prototype. And so what you can see here, we've got an IMX6 board on the right-hand side, and then we've got one of our 8-tuner boards connected to it via PCIe. And on the left, we've got a 12 terabyte NAS. And so this is sat on my desk at work, so I've got a 12 terabyte DVR sat on my desk. And this is our user interface you can see in the background here. And so what we've got is we've got the dark blue recordings over to the left. That's all stuff which has been recorded. The light blue is what's currently live and is being recorded, and all of the grey stuff is all the upcoming bits and pieces. But this is our sort of demo UI. We're sort of working on newer versions of that, but it's been working quite well for a while now, and it's really quite nice to use. Now, a few interesting statistics on the NAS is that so we've had that one running since the 13th of November. And so it's effectively been up for about 70 days when we took these statistics. And so we recorded 1,500, 15,784 programs in total. And of this, we had 1,375 unique movies on there. So there's a database from 30 days of 1,375 movies. So it's quite good if you just want to go and find a movie to watch. Right, so just a quick overview on DVB-T. So DVB-T is transmitted as multiplex data stream. And so I'm sure most people understand what that means, but effectively what it is there's several channels transmitted per multiplex. So you only really need to tune into one frequency to get several channels. So in the UK, and I should mention that all of our tests really have been carried out in the UK because it's where we're based, but because it's DVB-T, it should work in other countries, but all of my explanations today will be based on the UK. And so what we can see is in the UK, there's a BBC A multiplex, and that carries BBC 1, 2, 3, 4, CBBC, News 24, and others, and then it's also got radio channels on there. So in effect, if you want to record all of those channels, pretty much most of the BBC stuff, you just need one tuner, and you can just tune to a frequency. So just one of these silver boxes on here handles all of those channels. All you need to be able to do is just to get at the data. So what you can do is you can either record the entire mux, so just pull everything down into one file, and then you can demux it later using something like MPlayer or VLC, or you could demux it on the fly. And Linux, fortunately, has support for being able to do this. It's sort of virtual demuxes, as it were, is the easiest way to describe it, because you can pull multiple channels out from one demux into several different files. So the very last thing on here is 30 channels. Now, I say here 30 channels, but in reality, we can actually record with this hardware, we can record 128 channels. But the reason I'm saying 30 channels is because once you look at the channels broadcast in the UK, this is the channels from Freeview in the UK. This is taken from the Freeview website, and this is their entertainment section. And if you look on here, there's quite a lot of +1s or +24s, or there's things like over here you've got the so you've got the jewelry channel or community channels. It's just once you get rid of some of the things which you probably don't want to record, then you end up roughly in the UK with about 30 channels with good content. So, so that's why I refer to it as a 30-channel DVR. So now you might wonder how much data we're pushing out through this. And this is just one of the graphs taken from Munin for a day's recording. And as you can see here, it's 8 megabytes constantly being written out to the hard disks. So I know I said that I wasn't really a hardware engineer, but quite often my desk will look like this. And as you can see here, what we've got here is one of our PCI cards, which is what we've done here is we've got the tuner can missing, so that we can actually get at the circuit boards here. And here we've just brought out the pins, and so we can put a logic analyzer onto here so that we can debug the I2C. And for those who don't really know, I2C is basically, it's a low-speed serial bus. And it's how most tuners communicate, really. So moving on to our hardware development history. And the way we got started out was the first version just used readily available tuners. We found a Taiwanese manufacturer who had some chips available, but there were no Linux drivers. They only had DOS and Windows drivers for them, and the example tuner drivers were all given to us under NDA. So the issue with using these tuners was that we probably couldn't have released any product without violating some issues. And when we first built the cards, we were using their network interface modules. So the first card was really just to prove to us that we could do what we wanted to. And the other major issue that we had was trying to get some tuners from people. Most people would talk to us or would refuse to talk to us because we didn't want to order in hundreds of thousands of tuners. It was quite hard to convince anyone to talk to us. So the second version then uses DIBCOM tuners. It actually uses the 7090p, which is in quite a few USB sticks around if you bought one of the USB tuners. And the advantage of that, the main advantage, is DIBCOM tuners, the tuner drivers are in the main kernel. And rather than using their network interface modules, we could take their chips and put them onto our own custom network interface module. And so we have a modular board, and we can just redesign our own NIM if we ever need to. But we just made a slightly smaller NIM to be able to fit all of the tuners onto our boards. So here's a photo of one of our boards, just to put it up there. So you can see there's 8 tuners on this version, and the reason the metal cans are on there is purely for RF reasons rather than secrecy. So moving on to the Linux driver development. So I was never really hired as a Linux driver developer. I initially joined the company to maintain some embedded distributions and build up some embedded devices, and to do mostly Perl programming, really. But I did have a background in embedded C. I'd been programming C and assembler on the Intel 80251 for various other companies. So moving on to the kernel, it wasn't too much of a stretch, really. But what happened was we first of all started asking around, trying to find people to work on it. And we just found the costs of getting somebody in to write a driver for us was really just a bit too prohibitive. And during the process of going around asking and trying to find people to write drivers for us, we started to look at the drivers ourselves just so that we had the correct sort of knowledge for when we were talking to people. And so the first sort of stage that I got into was I was looking at a virtual driver. Now, so Linux has a virtual front-end tuner driver. You can see it there. It's within the DVB front-end section of the kernel source. It's just called DVB_dummy_FE. And that is essentially a virtual tuner. So it's a virtual one of these silver cans. And so we could take that and build a virtual DVB device. All we needed to do was to write a virtual bridge, as it were, because if you want to write a USB device, you have to write a virtual USB bridge, which then loads in the DVB dummy driver, and again for PCI. So we started off by writing a virtual PCI bridge, and the way that I got into testing that was I found an old graphics card, and I dug around in the kernel. I found its PCI ID, and I changed it so that it would load my driver instead of loading its driver. And so at that point then, when the kernel detected the graphics cards, it was loading in my virtual DVB-T driver. And we could test this driver by writing in a DVB-T file from user space and reading back. So if you want to get into kernel driver development, I strongly suggest having a look at the virtual driver and see if you can write yourself a virtual bridge. If anybody's interested in seeing the code, I can probably send you that if you want to email me. But I strongly suggest having a go at writing it yourself so that you can get into driver development. So moving on from there, once we had the virtual driver, we then went on to making the so-called NDA driver, one which we were never really, one for the card model, which we were never really going to sell on. And so I had to spend quite a long time studying the DOS driver code which we had and porting it to Linux and replacing the virtual front end in the PCI driver which we had. So it was quite handy to have already written the virtual driver because we already knew that our card, when we got it, would load up the virtual driver. So it was just a case then of trying to get it to call the tuner code. And once we'd got that set up, we then had to spend a long time studying the I2C and adjusting timings really until we got it to work. But once we got it working, it did just work. It was a way that the drivers in the I2C is set up. You just need to send through a lot of instructions down to the chips of I2C. So it's just a case of following through the code, looking at the instructions, and tracing it. So, moving on to our sort of open source driver. So what we did was we go back, we take the original sort of bridge code, as it were, the PCI bridge code, and we then added dependency on the DIBCOM chips, which means that the only thing we need to put into our own code, really, for the PCI driver is just some setup code, various different parameters that we need to pass through to the DIBCOM drivers. And again, then we spent a long time studying the I2C. And we actually got some time, we reviewed it with DIBCOM, and they pointed us out a few things that were going wrong. And eventually then we got those drivers working. And so now it means that adding support for other chips with Linux drivers is reasonably straightforward for us. If we move to a different tuner manufacturer, it's quite straightforward. We just have to repeat the process of adding dependency on their drivers and perhaps including some more setup code, and hopefully it should be reasonably straightforward. So, upstream. Now, this is a bit of a question mark because it's hard when you're working on a project to convince people to let you push everything upstream. And I sort of really got the sign-off at the end of last week to go and push our drivers upstream because we're not selling the cards yet and things like that. And whilst I really would have liked to have got drivers into the main kernel so we could get things testing, because I'm quite sure we've done a few things wrong and we haven't really found that out yet. But I was getting it ready at the beginning of this week. I uploaded it onto one of our test systems and had it running for a short while. It looked to be running great to me, and I thought that by the time I get to FOSDEM, because I was traveling around a little bit first on my way to FOSDEM, by the time I get to FOSDEM, I'd be able to push the button and release the driver, send it upstream, and all of that. And then I got a message saying that there are some issues with that machine. So at the moment, I haven't pushed the button on sending things upstream just yet, but once I get back, I can look at our machine, I can see if there really was a problem and figure it out, and hopefully on Monday or Tuesday of next week, we'll be sending the drivers upstream. But if you wanted to look at the source at the moment, if you give me your email address, I'd be more than happy to accommodate you. Now, so over the years, we've had a couple of different models of the systems. And so the left-hand corner, the pizza box style machine was the first system we put together, really. And it was x86. It's a straightforward machine. But the machine above it is more interesting. The circuit board that you can see there, that's actually an Ultimate RD. And it's a Marvell chipset. So it's ARM-based. And this is our first foray into ARMs. The only problem with that board is that it can either have PCIe or it can have video. So it's a little bit useless as a DVR, but what we could do is we could put our card into it, we could put a hard disk into it, and we had it recording 30 channels without any issues. We just had to pull the streams off over the network to be able to watch it. And the system on the right is one of the later models, and this is just a HTPC case. It's fanless, it's quite nice, a bit more of a beefy CPU, and it was just nicer VGA out. But it was really just allowing us just to test the hardware and test the software, just make sure that everything was running okay. So then we're moving now on to the i.MX6. And why did we really go for that CPU? First of all, there's a choice of single, dual, or quad-core CPUs. And it's also one of the few chips out there that, at least what I'm aware of, or as far as the hardware engineers have told me, that has PCIe support. And the chip is readily available. It comes as a computer-on module. So, or we can get it in computer-on module format, which is the way that we use it. And there's support from Freescale and from the vendor who we use for Ubuntu, Android, Yocto. I'm sure there might be a few others, but those were the main ones that we were aware of. And the MX6 also has H.264, MPEG-2 decoding and encoding. And most of the video is all controlled through GStreamer on Linux. So before we moved on to that, we had quite a good idea that it would be very nice for systems. We'd be able to run Linux on it and use GStreamer. So we were confident that we could start to make things work. So the issue then came down to which distribution to use. Now, I'm a Debian guy. I run Debian pretty much everywhere. This laptop runs Crunchbang, but that's a Debian Driviant, and I'm really a Debian fanboy. So it was quite hard for me to eventually admit that we ended up with Yocto, but basically what happened was when the i.MX6 hardware arrived, the machines, first of all, we booted them up with Ubuntu and we tested that the video worked. So that was great. We had a nice video coming out and we know that works. So then we built the Yocto images, which are provided by the vendors, and tested video again. That works great. And so from that point then, we took the Yocto kernel config and we built the vendor's kernel for Debian with PCIe support, which was included as standard, and also included our driver into that kernel. So then at that point, we had Debian booting on the i.MX6, and it started recording DVB-T. So that was great. We had the i.MX6 recording 30 channels, working without any issues. So that was really nice. But then, as my own omission at fault, was that we failed to manage to get the Freescale video codecs running on Debian. And the trouble with that is we don't have too much time to spend on trying to get everything working. And I was looking at the the codecs, I could get them to compile okay, they would build fine, but for some reason then GStreamer would never work correctly with those codecs. So it was just a matter of time that I had to go back and look at Yocto, and then at that point I added our kernel patch to Yocto, and at that point then we had both video playback and recording working on Yocto, and due to a time constraints, it was obvious that Yocto was the easiest way forward. And then after a few days of running our system, I noticed a large performance advantage with Yocto. I have been meaning to spend time to go back and figure out what the difference would be between the Yocto build and a Debian. I'd hoped to spend some time over Christmas, but I was unfortunately a bit ill. So I checked the obvious things like whether or not we were running on ARM-EL or ARM-HF and compared them both. And everything looked to be perfectly fine, but there was a noticeable performance advantage with Yocto when running our software. It wasn't the standard running of the system, it was just when we built and compiled our software on there, the actual recording, it just seemed to use a lot more CPU on the Debian system. Now, to recap, for those who haven't come across it, Yocto is basically a system that allows you to build your own distribution. And that's just a quick quote from the Yocto project. But moving on, I'm not going to go into Yocto in too much detail, but I'm just going to give out our tips and tricks for getting on with it. So my major tip for Yocto really was to fully check through the repositories for software. There were quite a few times when I thought I was looking through the repositories and I thought, oh, they don't have this bit of software, I'm going to have to go and build it myself and spend a lot of time, and then I'd start looking at building it, and then I'd realize that it was actually hidden away in a different repository. So what you need to do is you need to look at the repositories in bblayers.conf. And this is an example. So this is our BB layers. And as you can see from down here, you've got all of these repositories with things like Meta Perl, Meta Multimedia, Meta Networking. And for some reason, networking is separate from web server. So you might think you go and enable networking and you might be able to just install Nginx, but no, you need to go and enable Meta Web Server. So you really need to keep an eye on what repositories are available to you and make sure you enable them in bblayers.conf before you start trying to add software into an image. And so then one of the important things that you can do is that you can add packages to an image. So when you first build an image, it's got a certain amount of packages in there. You choose a multimedia image and it includes GStreamer. But then when you want to add in some extra packages, you can do so in local.conf. So this is an example from our local.conf. And this is just, this is a small section of it. So what you can see here, these are all the extra packages we request. Things like PostgreSQL and GStreamer, some extra bits, OpenSSH. And down here, one of the important things is package management. You really need to add that in if you want to put some packages onto the images yourself after you've built the image. So once you've built the image, you can use the Smart Package Manager to be able to add some stuff in. And so you can just go through this process. On your build machine, you can run bitbake. And so you can search through the software packages available with that first line, just looking for software. So you can search for Nginx, and then once you found that Nginx is available to you because you've enabled the web server repository, you can then just build Nginx and make sure that you update the package index. And once you've done that, you can then, on your target, you can use Smart Update, and then you can search for Nginx, you can install Nginx, and very importantly is once you've got it installed, you can then look at the paths using smart info and figure out exactly where everything's gone, because Yocto doesn't necessarily put, or the package might not necessarily put everything where you expect it to go if you're used to Debian. So moving on to Qt development. Now, Yocto very nicely provides a tool chain, so it's quite easy to get into Qt development. You don't need to build your own tool chain. You can just build a Yocto package, and then you've got a tool chain you can install on your build machine. So you can then use Qt Creator on the build machine, and you can run and debug code on the target, which is really nice. It's really very straightforward. And the advantage of using Qt is that it's cross-platform. One thing I didn't perhaps mention earlier was that on the other versions of the DVR, we've done the x86 and the previous ARM, it was all running the Qt software. And our Qt software would just also runs on Windows and OS X. So you can pull up the same interface that you get on the TV on your Windows laptop, on your Linux machine, on your Mac laptop, and watch TV. And if you need it, we haven't had to go that way, but there is support available from Digia and Qt.io if you really need it. So there's also a WebKit module, and we use WebKit for our HTML5 UI, which again is quite nice. Having a HTML5 UI means that if you don't want to install software on your desktop, you can just pull up the website, and because in our JavaScript you can obviously tell that you're not running on the local machine, you can do interesting things like adapting the interface so that you can then start playing the software from your laptop instead of having to find your remote control. So it's quite nice. And of course, Qt has GStreamer support, which is necessary for this project. So moving on to GStreamer, and I'd say I'm quite new to GStreamer, and it's quite an interesting project to get into. It's essentially an open source media framework. And I say here it's not a media player, and that's because you can't use it like Totem or MPlayer or something or things like that. You can try to, but it's more of a media framework for building applications. And when you're playing around with this, what we found was that Playbin is your friend. So Playbin allows you to, Playbin will automatically try to guess what your multimedia pipeline should be. And it's very useful because you can just use that and you don't need to pull together your own pipeline. So GStreamer can generate the graphs of Playbin pipelines, which again is very handy because what you can do is once you configure, if you need to do a custom pipeline for some specific reason, then you can run GStreamer with Playbin, you can generate a graph of it, and you can look through and you can build your own pipeline. So in order to do that, you need to be able to set the GST debug dump.dir variable, and then you can just run GStreamer or GST launch as usual. So you can see here it's GST launch with Playbin, and we're just passing it in a file URI. So this is, I'm not sure if you're going to be able to see this that well, but this is an example of the graphs you can generate from GStreamer using GraphViz. So basically, this is a HTTP file being passed in, and is going into a type find element, and then it goes on to the, now this is the Freescale IMX6 demuxer called AIUR demux. And you might be wondering why we would be demuxing again. And that's because when you have a DVB-T transport stream coming in, you will separate out the channels, but the channel will still be a MBEG2 file. So you need to demux your audio and your video out to continue. And as we follow the pipeline down, what it will do is it goes through a multi-queue and it ends up being separated out so that you've got the audio being passed by a GStreamer module, and you've got the video going down into the VPU decoder on the IMX6. So then, as you can see here, what we've got is the audio decoder of the IMX6 up in the far left, and down here we've got the final video output, which is on the IMX6. So these are all Freescale plugins which are being called within GStreamer. And it's just using the ALSA sync output there. So that pipeline, if you wanted to put it together yourself, would look something like this. So that's why it's quite nice to be able to break out the graph and try and follow it through. And so you can just adjust some of these if you want to, some of the variables, and carry on. So that's how we managed to build our DVRs. So, any questions? Interesting question. I don't know yet. It's not been fully decided. We had a couple of manufacturing delays. So we've been putting it off, but we'll be announcing the prices soon, I think. So, sorry, yes. At the moment, they're not HD capable. Sorry? Yes, sorry, it's just been asked, are the cards HD capable? And at the moment, they're not HD capable. And the reason for that is, again, trying to get hold of HD chips has not been the easiest thing for us to do. We've now got some HD capable chips from some manufacturers, and we're building them onto our cards. But the reason for the delay in not having them on was simply getting hold of the chips. So we'd expect within the next few months we would have a HD card ready. Yeah. Sorry, yeah. So is it just a card, or do we have a user interface, and what exactly is a business model? So what we've done is we started off from scratch with the cards, and we just plan to sell the cards. We don't intend to sell any, or we don't intend to provide any software solutions. There's already a lot of very good Linux software out there for DVB-T recording, and what I want to do is I'd like to be getting more into those communities and helping out and make sure that our cards are working with their software, rather than us providing yet another bit of software for people to run on their systems. So, for instance, we'd like to support people with running TV head end and things like that with our cards. And what we're trying to do is with this system, we're trying to build up so that we sell an entire box, an entire DVR, and that would have our own recording software on there. And I'm not entirely sure what the release date is on that. It's why I said that I worked on the kernel driver, which is open source, and on the user interface section. That was our demo user interface to prove that things would work, because there's not much other software that records everything all of the time. And that's what I'd like to start doing with some of the other projects. So that's the way that we're carrying on. So, yes? Yes, there are some difficulties with looking at things like cable and so on, because we haven't spent much time looking at it, but because there's many more muxes transmitted on cable, so it's, as I understand it, it's slightly more difficult to be able to record everything with DVB-C. But having said that, we do want to put the next generation of chips we're looking at. They would already support DVB-C and ISDB and quite a few others. The new chips which are coming along, they support many more DVB methods. So I'd like to think that we should be able to do DVB-C in the future. So, yes. Yes, but I'm not sure of the cost of pulling in sort of 8 USB sticks and getting them into a manufacturer and then pulling all of that data down over the USB bus. It seems to us to be more logical to go down the PCIe route and be able to sell our own hardware. And then move, because we started off building our own hardware first and then moved on to looking at the building DVR boxes. So, yes. So. Yes, yeah. Yes, sorry, sorry, you're asking, if I can repeat the question, you're asking how does the driver talk to all of the tuners, is it? Or what does the bridge section? So, okay, so what did I have to add to the driver to do things? So basically, my driver controls all of the PCI stuff. So we have an FPGA on here, and so my driver talks to the FPGA. And so what I have to do is I have to be able to take the information from the DVB-T drivers, so from the DIBCOM drivers, and be able to pass that through down to the FPGA. So that's how the bridge works. And the FPGA will then pass it out to the individual tuners. Yes?
You mentioned the hardware
Sorry?
You mentioned the hardware DMUX?
Yes. Yes. So sorry, I was asking about the hardware DMUX. The hardware DMUX is in the FPGA. Yes, so again, asking about individual channels or the whole MUX. And actually, our hardware is designed so that we can do both. You could actually request just 1 or 2 channels from a DMUX, and at the same time, you could then also request the full DMUX. So you can get everything, really. Sorry. Yeah, that is something that we're aware of. In the UK, we're very lucky that it's pretty much all unencrypted, apart from the there's some channels which are encrypted, and the DVB-T2, the EPG on the DVB-T2 is encrypted. So we'll be having to deal with that when we get onto the DVB-T2. But we are aware of the need for CI, so we are looking into CI support. So, and I think we're out of time now, so thank you once again, Philippe.